Thank you. Okay, so
spend a little time just, oopsie daisy, touching on thermal stability because it's so important. And this actually touches on what Hans Christian said, right? So much of the solution depends on gain. The primary driver for the difference in gain is the temperature. So you want to take advantage of a thermally stable environment. So this is the first year of WMAP. And this is from Lamont et al. Here we go, I think, good. First year of WMAP, and just look, these are our reflectors here. Oh, you know, not quite a half a degree variation over a year. This is our passively cooled focal plane array, so near 90 Kelvin. And again, not much. You can see we had, these are actually temperature variations from solar events showering the primary. So this is the first bolometer experiment at L2. Right? So that's what all these are, and then station keeping and things like that. Okay, so that's great, right? And as we all know, we're designing an observing strategy. The game is to play off spatial coverage with the time scales at which you cover some given angular range. So this is, I love this plot from Norm Jurassic's paper. So this is, and this is you want to design your system. You just can't do this from the ground, right? To have this kind of stability. So WMAP in particular, right, we had a constant solar insolation. And we really took advantage of it. So this is a thermometer on the primary. And this is just binned in the sun azimuth, solar azimuth. And this is, as you can see, that is 150 microkelvin. And that's over 3 years, right? This thing is just a rock, right? The gains from this term aren't changing, right? So this is this is the sort of thing you can achieve in space. And then here's another one, and this is, and I should actually say for the cosmic rays, this is something, say, for LightBird, sorry, not cosmic rays, solar flares. For LightBird, if you have the half-wave plate, which lots of advantages to it, but you'll see them in the half-wave plate, right? But this is another thing, right? And this took, and especially with LightBird, I should say I'm a LightBird proponent. I think it's a fantastic opportunity. But whoopsie daisy, but look at this. This is over time, so this is from one of Chuck's papers. Over time, just the center of the passband changes, right? And now you've got to design a system. You want to design a system to make sure you can isolate this from everything else, because your foreground signal is going to, what you call foregrounds, is going to change. And for LightBird, the challenge is foregrounds, right? They're huge at these low Ls. We've already measured them. But you need to design it to take advantage of this. Okay, so, and then of course, why V-band? You mean because it's different? And so I was actually trying to think back, maybe Chuck will remember. This has got to be the transistors in the amplifiers. It's not something else, and they were all handmade, right? So I'm guessing it was something like that. So, good. So for space, I mean, just to say the obvious, right? You make all sky measurements in frequency bands. You have to do this because these are legacy surveys that you can't access from the ground with roughly photon limited detectors. But I also, so this is great, it should be done. And as I said, I really hope it does get done, and LightBird's, at least from my vantage, the next best opportunity. But there's a lot of complementarity from the ground, and it's changing, it's improving. I'll show you some. So from the ground, right, we already have measurements in T and P above L of 500 over large areas that are well past Planck's sensitivity. And that is just going to improve. And in some ways ahead on systematics, because we can observe Jupiter, say, or Uranus or something like that whenever we want, and we can really dig into the beam and its polarization properties when we have to. And then we're pushing this to low L, and I'll show you. So this is this is a white noise level from ACT. This is the latest release, a plot from Sigurd Ness. So this is in temperature. And I should say this is, so ACT is now, whoops, see daisy, ACT is now turned off. In this case, it was, this latest release, or DR6, was Suzanne Staggs was a PI, Mark Devlin was the co-lead, and Joe Dunkley ran the analysis. But you can see here, if I get my pointer right, good, that's Planck right there. That's where we are over a good fraction of the sky, 16,000 square degrees. And that's how far we have to go to about a factor of not too far from where SO will be, and then below that where CMBS4 would be. So that exists. That's now, so this great sensitivity. And if you look here in polarization, the sensitivity is even greater. Okay, so, and this is just going to continue to grow, right? So you really, so in thinking about the future and this complementarity, you just want to plan on there being huge sensitivity from the ground. Okay, so, and here's another, I wanted to drop this in. So we had sort of the two lead papers were Calabrese and Hill. Armenia here can correct me if I say something wrong, and Thibault Louis et al. Taking those data, the DR6, and comparing them to, getting the cosmology out of them, of course. But and just thinking about all the discussions, BAO tensions, Hubble tensions everywhere. That look at just. For the CMB, this is, you can glance over those. These are parameters that we do particularly well on. But well, you can see this is ACT alone, almost alone. We use the Planck tau prior. But there's Planck in yellow. And there's that red, except for that prior, has no Planck in it. That's WMAP plus ACT, right? So completely with that asterisk, independent measurements. Different detectors, different people, different pipelines, different strategies, different everything. And you can just look at that visually and see not only are the errors comparable, but they agree phenomenally well. And that's just across the board. Here's how you know, it's hard to read tables in a talk, but there it is. Just take any line and scan it. And the agreement between whether you take ACT alone plus the prior, Planck, WMAP plus ACT right there, Planck plus ACT plus lensing plus baryon acoustic oscillations. It's the same, right? This is, there are not many, there's small pushes in there, but that's just, to me, this is sort of mind-blowing, right? Because they're all different. These really are different, right? And Planck was different than WMAP, of course, and different than ACT. And I should say, SPT will, they've had a bunch of releases. I wish John Carlstrom couldn't be here. Maybe Jamie will say something. But it will do, we expect it to do the same thing. If you look in the past, it's all been tracking, right? So this is an amazing thing for CMBS 60. It's just, I think this is really quite a state of affairs. And here is, here is this plot. You've seen them all together. And you can see there are three little thin gray lines there. So when people talk about different models, one of those is WMAP, I've forgotten which one. One of those is Planck, and one of those is ACT plus either one of those. You couldn't tell. That's, in terms of the models, those are the differences we're talking about. Right? It's nothing. Down here, the error bars are so small, you can't plot them and see them above these models. Right? This is just amazing precision. And And you can see here, this is, the data has been mostly above L of 500. SPT's been able to push to lower L's because just the atmosphere is easier to deal with at the pole. But I wanted to emphasize a couple things. I mean, I think the weakness or the soft spot in all this and pushing ahead is measuring tau. And there are a few efforts. Sylvia and Paolo are trying to get an effort launched here, which is really important to measure tau from a balloon. Bill Jones and company with Taurus, unfortunately they got doged, and so that will hopefully recover, but that will be another one. This is a recent result, Chuck mentioned it, from Yin-Yang Lee, Joseph Weimer, Toby Marriage and company from class, and those are the dark purple lines here, and this is the magenta ones here are just Prince and Dunkley's maximum likelihood addition for Planck. But you can see through cross-correlation, they're really starting to get to these low L's, which is exciting. I don't think we can ever get to what space can get to down there, but of course you've got to keep trying. But this is, but this will keep going. So this is very exciting, and all these are getting smaller error bars. And so this is just to start to say this is just filling out the picture, going to lower L's, and we all, BICEP is setting a standard here for sensitivity and sky coverage, but you'll see in a minute we're all trying to understand those low L sky better and better, and any space mission should just make sure it complements that, right? And take advantage of that. 5 minutes, good, okay. Okay, so here's a map of, so this is a preliminary map, it should sound good, preliminary, from these small aperture telescopes in Chile, and where's Susanna, maybe here somewhere, she made this map, and you can just see, so this is at 90 gigahertz, so these are receivers, and the ones that have been taking data are taking data at 90 and 150 gigahertz, and this is just a fraction of the data we have, but you can just look at it and see there's Q and U, right? That's it, right? It's to the eye. It's easy. We can take the power spectra. We know how low in L we can go. This is straightforward, and the thing to keep in mind, right, is I think this will be especially nice to complement, say, a LightBird mission, right? Because it's large angular scale. You can compare, over a very large scale, you can compare a lot of sky between space and ground. And to give you a little, so you can make these measurements from Chile along with all the other ones I showed you. And to give you a sense for how a modern measurement is made for those of you who aren't making measurements, so on Wednesday, yeah, we're taking data, right? So this is a receiver that's sitting up at 5,200 meters with a dilution refrigerator cooling the focal plane to 60 millikelvin. It's been stable for a year. Stable to a few millikelvin per year with a spinning half-wave plate, right? Many of the things you talk about for LightBird. And you could see the way things work is it was on Wednesday, actually Sam, Sam was monitoring it, right, from here. A hose burst, or started to leak. And so got with Kyohei Yamada, who was back in Princeton, stopped the half-wave plate, collect mixture, right? And this is distributed all over around the world. Collect mixture while I was sitting here listening to Andre. And, and then the guys at the field will repair it and it'll come all back up, right? So these things are now operated remotely, doing pretty sophisticated operations, and just churning out these data. Okay. So the future is really bright for ground-based measurements of B from Chile. And let me just tell you what's going on right now. So this is the Simons Observatory. And it has the sort of the core components. This is, the leads here are Mark Devlin and Suzanne Staggs. And here's the large aperture telescope. It has now had first light, so that's like ACT, but it's about 5 acts, so that's coming on strong. And then here are 3 small aperture telescopes. And so 2 of them have been taking data, a tiny fraction of which you saw in that map. And this is what's under negotiation right now. Many of these are being built. There are 2 more sats being built in the UK, so those are happening. There's another small aperture telescope. There's another one being built in Japan. A French group is talking about building them. Another one, so now they're adding, under Mark Devlin's really taking the lead on this, adding a whole solar farm, so we're getting away from diesel generators. And maybe, we'll see what happens with S4, but there's room for more receivers down there. So this is going to be a very powerful site, and it's and we're just going to keep pushing ahead, right? And it'll be, again, just a great complement to whatever happens in space. So let me stop there. Thank you.
So, unless there are immediate questions for Lyman, I will call Francesco Piacentini, who is going to present state of the art of Lightbird.
Okay. Yeah, okay, so I'm going to talk about a bit of technical or, technical status of Lightbird, and later today Tomo will talk more about the scientific goals. But in a snapshot, Lightbird is in its name is the satellite for the study of B-mode polarization and inflation from cosmic background radiation detection. So it's a space mission for CMB polarization at large angular scales, with a target of delta R, order of 10 to the minus 3. So the instrument is being revised, as I'm going to say, but this is the status about 1 year ago. This was the status about one year ago. 3 telescopes, LFT, MFT, and HFT. You can see them, LFT, HFT, and MFT. Each of them with for a total 40 to 400 gigahertz frequency coverage, and TS detectors at 100 millikelvin, 3 cryogenic rotating alpha plates for polarization modulation. The LFT is led by JAXA, 40 to 140 with a reflective optics and sapphire-based alpha plate. And the M and HFT, European led with CNES, led by CNES, covering from 100 to 400 gigahertz with refractive optics and metamaterial-based alpha plates. So it's a very complicated system. The sensitivity, the baseline sensitivity, is for a map depth of the order of, okay, there is the map depth plot there with the best sensitivity map depth of 4.6 microkelvin per minute and a combined sensitivity of 2.2 microkelvin per minute with an angular resolution of the order of ½ degree, so aiming at the large scales. And one of the key elements is the polarization modulation unit, so we would like to modulate the polarized fraction of the signal because we are looking for very, very tiny signals. So modulation is a key element to extract signal from noise and from systematic effects. So the alpha plate basically, it rotates and modulates the polarization at 4 times its rotation speed, and these allow extraction of the polarized fraction. introduces the impact of 1/f and systematic effects. There is no need, this is a very important point, there is no need of combining different detectors to extract polarization that we have seen in Planck that it's potentially problematic because any difference between the detector performance like gain, beam, time response, bandwidth details is going to affect, when you make the difference, it's going to affect the result and generate fake polarization. So using the alpha plate, you can, with each single detector, you can measure the polarization, and that's a big benefit, especially if you want to look at the larger scales. The combination of the alpha plate rotation with the scanning of the satellite will slightly move the band of the polarized signal just next to the 4 times the frequency of the alpha plate. So even if there is some systematic effect exactly at 4 times the frequency of the alpha plate as an harmonics, this can be notched out. Okay, the idea is here. So the magnetic freezing, there was a video which I think is not working. No, it's not working. But it's a YouTube video showing how the freezing of how our superconductor is frozen in the magnetic field of a magnet. And okay, so this is easy to say, but very difficult to make. So there is a big effort in doing continuously rotating alpha plate for a mission lifetime of 3 years with a stator, which is the superconductor at the temperature of 5 Kelvin, and a rotor at a temperature below 20 Kelvin with a rotation speed of the order of 1 Hertz, and an allowed heat load on the 5 Kelvin stage of 4 milliwatts, so very limited heat budget allowed, and an encoded accuracy of less than 1 arc minutes. So this is a prototype for the MHFT previous telescopes. These are other videos. Yeah, okay, this is a prototype actually spinning, you can see here. And here another video with the system spinning. This is taken by Fabio Columbro in Scienze et al. Now, we are facing a reformation plan. So what's happened in last year, 1 year ago, or a little bit less than 1 year ago, the KK decided to step down from leading the role in the procurement of the TS detectors for LightBird. So that was a big shock for the collaboration. And in September, last September, ISAS JAXA at a key decision point with the decision taken that the LightBird collaboration will conduct investigating the formation plan for about 1 year. And then ISAS JAXA will judge the continuation of the project in late 2025. So now we are facing this reformation. In October last year, the LightBird PIs has changed to Tomotake Matsumura, which is here and we'll talk later. And we are investigating alternative procurement plans for the KK detectors contribution. And also in parallel, the international team is actively conducting reformation investigation for optimization, simplification of the mission. So the main points, the building the detector plan in coordination with new partners, revisit the overall mission design, while keeping the science goals, revisit the science objectives with review of the error budget, simplify the mission configuration, simplify the cryo chain, and also, since as Ishiro mentioned, it's also a beauty contest to convince agencies, so we would like to extend the science possibilities, including synergies with the ground-based CMB data. So that will be presented by Tomo, but basically the science goal, the primary science goals remains the same. Covering the full sky with an angular resolution of the order of alpha degree from 40 to 400 gigahertz. So what, okay, before this is the 3 instruments we have seen before, and the idea is to combine the 3 into a single telescope and a single instrument, so a big simplification in this sense. And this is allowed, among the other things, by a study by Gianpaolo Pisano, a prototype of a alpha plate with a very large bandwidth, which can achieve 10-to-1 frequency coverage, so 40 to 400 frequency coverage, while before it was order of 2.7 to 1. So that was one of the reasons to have 3 instruments before. Now we think we can do 10 to 1, so we think we can fit 40 to 400 gigahertz in a single instrument. This is a big change. You see the modulation in red. The modulation efficiency is not perfect across the band, so there is a price to pay. But still, this is reaching the sensitivity that we need. Okay, so we have been studying 3 designs, basically. An option 1, which is a single reflective telescope, similar to the previous LFT, without alpha plate. So we are also studying a case without alpha plate, with an extended coverage from 40 to 570, and with a faster spin rate of 1 spin in 3 minutes. And this is, of course, nice because it removes this complex system, which is the alpha plate, but at the same time, it's sensitive to 1/f to systematic, so it's a bit problematic from this point of view. Then there is the so-called option 2, which is similar optical configuration, but with a transmissive alpha plate on top, 40 to 400 gigahertz, and with a nominal spin rate of 1 spin in 20 minutes of the satellite, while the alpha plate spins around 1 hertz. Then we also have been studying a configuration with a reflective alpha plate, which has some advantage because it can reach 13 to 1 frequency coverage, so even wider frequency coverage, so better performance for polarization, but for physical constraint, the focal plane has to be smaller, so again there is a trade-off, so you have better performance of the better sensitivity per detector, but less detectors, so this is another trade-off. And a complication, possible complication induced by the reflective alpha plate, which is, at the same time modulates the polarization, but also is an optical element, is a mirror which can move the pointing and induce other effects at shot. So let's see what is the current status. We had the CNES key point, which is a sort of, not a formal review, but it's an analysis of the status of the mission in April. And so we decided, or we proposed a baseline with a transmissive alpha plane, so which the one I called option 2 before, so transmissive alpha plane. And we also have the option 1, which is the one without alpha plate as a backup. They are same optical design, similar thermomechanical design, so this is can be a simple backup. There is a plan to develop TS detectors in Europe with support by ESA DTEC, with main contribution from Italy, UK, and the Netherlands, and more contribution from France, Spain, Switzerland, and Finland. There will be this second key decision point in September, which is coming soon, so we are preparing for that. And JAXA, the decision point is for JAXA to approve the mission continuation. So this is very important. Then there will be a JAXA mission definition review in the spring 2026 for confirming the activities and define the instrument, the mission design. A point on complementarity with ground. I mean, I'm stating the obvious here. With space-based, we have full sky observation and sensitivity to the very low L, which I think is very difficult from the ground, even if we have shown great results. Wide cover frequency coverage, larger than what you can do from the ground, especially in the high frequency side. While from the ground, you can use cutting-edge technology, more detectors, you can update your instrument, and so on, which cannot be done in flight. The sensitivity can go to very high L, so a great complementarity in this sense, and technological exchange is very important to achieve synergy. And there is currently a memorandum of understanding between Lyrebird and CMB-S4. The goal is to quantify this synergy and make forecasts on the projected sensitivities and so on. yeah, both ways, say. In summary, LightBeam is a JAXA mission for precision measurement of the CMB modes. Full sky maps with potential rich signs on top of the tensor to scale ratio. Is currently the only space-based mission observatory for CMB planned in the next decade. It's currently under reformation and will be like that until next autumn. To rebuild the detector plan and to make the mission more robust, simpler, and keeping the same science targets, and not to lose the opportunity to conduct the CMB mode observation in space, which I think, you know, it's a difficult and risky measurements, but you know, that's not a reason not to do it and not to try it. And here is the partners. Thank you.
Thank you, Francesco. Any immediate questions for Francesco while Jimmy comes for the next talk? No? Then let's move on. From bicep to pico, right?
Right. Okay, so I'm going to be talking about the South Pole Observatories, our program, which is very much focused on inflationary B-mode polarization. Originally, this talk was going to be on bicep array and complemented on the SPT side by John Karlstrom, and unfortunately, John's not able to make it. So this talk is a little unbalanced and focusing on bicep array. So our program began about 25 years ago with this grand challenge of looking for a B-mode polarization signature from a background of gravitational waves. And of course, as we all know, gravitational waves have a handedness, and so they can produce both E-mode and B-mode polarization, while the scalars, which are the dominant signal, only produce E-modes because they don't have a handedness. And so in this B-mode basis, we don't have the large sample variance and cosmic variance from the scalars. Okay, and I will start with ground and space complementarity by talking about the South Pole, which I would argue is basically the closest on the surface of the Earth that we can get to a space environment. This is the South Pole Station here, complete with an airfield, and it's on a high plateau, about 10,000 feet elevation, very dry, high site. And it has the feature that we get one night and one day a year, and we observe during the winter, basically. So the atmosphere at the South Pole is not turned up daily by diurnal temperature variations. And so the atmosphere is very stable, very quiet. As you can see on this plateau, the horizon is also very featureless. And the fact that it's at the South Pole allows us to do something we call relentless observing, which is basically we're boring a hole in the sky, observing this deep field, and it simply goes around in a circle every day. And so we can continuously observe this patch, and basically we've been doing that for 20 years now. And formerly, I would say the South Pole had excellent logistics for power, data, and cargo. It's been somewhat less excellent since the pandemic and has caused us some problems. And as we'll see for the future, this is definitely an issue for the future CMB S4. What you see here is the South Pole Observatories. Has a long storied history. The facilities you see here really began with this ground shield, and originally it was the ground shield and system for the DAISY experiment, which has made the first detection of CMB polarization. It was then replaced by Quad, then Keck array and the bicep array. Bicep 1 was installed in the roof here of this laboratory smaller ground shield, and it's been replaced by successive experiments. And then, of course, the South Pole Telescope, which is on its third receiver and planning a fourth. So as you see here, we've been making excellent use of existing facilities, existing telescopes, and basically upgrading our receivers largely in the focal plane while keeping the logistical footprint approximately the same. Okay, so let me take you back to 2000. And in 2000, when the field was thinking about how to do very deep searches for inflationary B modes, there were really two schools of thought. To use a large telescope, where you get everything, right? You get access to large scales for B mode search, because the signal peaks at 2 degrees, but also all the fine scale stuff with very small beams. And at the time, the systematics were concerned about beam mismatches, and so that seemed like a very good approach. We, with bicep array, did something quite different. We adopted this small telescope strategy, and basically the idea here is we have a refracting optics, very wide field of view, and the optics are cooled to 4 degrees Kelvin, and surrounded by absorbing materials. So it's a very low side lobe, very clean optical design, and then peeks out through the window here, large aperture vacuum window. So very low side lobes, excellent control of systematics. And with a small telescope, you can do a couple of other things. You can rotate the whole telescope, and that's also good for polarization measurements. And so you can see here with our mount allows us to spin, and we do that as part of our observing strategy while scanning and then stepping in elevation. The telescopes are surrounded by this absorbing forebaffle, which kills a couple % or so of stray beam on an absorbing surface, and then surrounded by a reflecting ground shield, which makes the temperature, reduces the temperature contrast. Of late, what we've been doing is going from these small aperture 26 centimeter systems to larger aperture, 55 centimeter systems, and it may not seem like a very big change, but it actually dramatically increases the throughput, the A and omega, A times omega, light gathering power of the system, such that depending on the band, we get of order of 15 times improvement in overall mapping speed. So here you can see on this mount an intermediate state where this is a small Keck receiver, and then this is a recent picture, and you can see 3 large bicep array receivers, which are filling in here. Okay, so you can see the progression. There was actually a bicep 1 stage, which used PSBs from Planck days. Then this was taken over with transition edge detectors. Initially, single color measurement at 150 gigahertz with bicep 2. Keck array was a 5-shooter of these smaller apertures, going from 95 up to 270 gigahertz. Bicep 3 is now the large aperture system, all at 90. And then with bicep array, we're planning bands at 30, 40, 150, 220, and 270 gigahertz. And right now, all 3 of these receivers are in the field, but the 220 system just fielded this year with a partial focal plane. Okay, so as it turns out, history has borne out this approach, and constraining inflationary polarization is really all about systematics. And so this is the history of error on R from polarization, and the red points are from the bicep et al. Program. And so you can see here, this last point in most recent point is actually from SPT with their first constraint on inflationary polarization. So this approach has been very successful. It is now really hitting the limit where we're limited by our ability to de-lens the maps. It's limited by noise from the gravitational lensing signal. And so you can see 2 forecasts here with accumulated sensitivity. So this data point here from 2021 was using data through 2018. We've now accumulated data through 2025. Through 2024, you can see that even though there's a big increase in sensitivity, we don't get very much improvement in our error on R, and that's just because we've hit the lensing limit. But with SPT, we can de-lens and progressively do that better as the measurements from SPT get more sensitive. And so you can see the forecast here with de-lensing. We really rely on de-lensing to have future improvement. This is the constraints on inflationary models that you've seen yesterday. And the thing I like about this plot is you can see now the constraints coming in with blue, and that reduction is really all due to the polarization measurements. And all these models of inflation, natural inflation, and so forth and so on, inflation with monomial potentials, with this measurement of n sub s, are heretofore popular models of inflation are actually excluded at the 2 sigma and above level. So that's really a first here. We're now constraining popular models of inflation. Okay, so here are some maps that we've been developing since this result that came from data through 2018. So the first thing is BICEP3 has been observing, doing very well. This is now 9 years of sensitivity, and our collaboration had a bit of a discussion because I wanted to show E and B mode maps, but they were unpurified. So we decided to show Q and U maps, but Q and U are really turning into the kind of things you see in temperature, which is they're just totally dominated by scalars. Okay, so all these patterns you see is just entirely scalars, and so you can't really tell the difference between this map and the other maps. I'll show you, but these maps now, because of the BICEP array field of view being bigger, are overlapping the very deep, smaller maps that we've made with BICEP and Keck array. So that smaller region is in the middle here, and then with the larger fields of view, we're covering somewhat more sky. Also, these maps now have a sensitivity of 1.65 microkelvin arc minutes. It's a lot more sensitive than Planck. It's actually a lot more sensitive than LightBird. And so we're basically at kind of pico level sensitivity in this patch, super, super sensitive. Okay, so here's the map made at 150 gigahertz with 2 years, and I think, as I said, you can hardly tell the difference, even though the 95 gigahertz map is actually a lot better. And then we've been adding a low frequency band to constrain synchrotron, so here's the map coming in at 40 gigahertz. The angular resolution isn't as good, but again, you can clearly see scalars in the Q and U maps. Okay, where are we now in terms of sensitivity? So this plot shows B mode sensitivity at the L of 80 band, where the recombination peak lies. It's in CMB temperature units, so CMB is flat here across the frequency bands, and the blue points represent BK18 is published, and our latest analysis on maps through 2023 are shown in pink. Here's the big improvement you're seeing here from BICEP3, doing a lot better. L means the large area maps. So the small area maps largely are coming from Keck array and BICEP. So at 150, it's really all coming from improvements in analysis. Keck array has been observing mostly at 220 and 270. And so that improvement, these are new, and then we have new data points here at 30 and 40 gigahertz. These are, of course, the sensitivities. You can see that sensitivity to dust, this blue band, is given by the ratio of the sensitivity to the line. And through arduous work, we have gotten to the point now where basically on the ground, we're constraining dust much better than we can with existing data. So here's Planck in this region. Synchrotron is a bit of a more complex story. You can see the WMAP 23 gigahertz band there, and we still don't have a detection of synchrotron B mode polarization. The new data coming in here at 30 and 40 hopefully will clarify the situation. Maybe we'll have a detection. And then, of course, here the solid line is where you hit lensed lambda CDM. Okay, so that gives you an idea when you're hitting the lensing limit. Okay, so then we all had a curveball looking into the future. So this is an edict that came from NSF. So the first part I'd like to highlight is the importance of CMB science in planning documents had done quite well. So CMB S4 was tied for number 2 in the decadal review, and it was the number 1 tied for number 1 for new construction in P5. P5 is high energy physics. So our colleagues in astronomy and particle physics thought we were a very high priority thing. So the community did quite well in terms of future planning. Unfortunately, NSF said that they cannot support large-scale infrastructure for planning CMBS4 for the foreseeable future, but they did say that they will continue to support CMB activities at the pole and in Chile. So I would just like to sketch out our proposal for a future plan. I should emphasize the word proposal. So this is still being formulated. Funding is not all in hand, and so forth. But going forward, what can we do at the pole with our existing facilities? And we're going to follow the same path, which is let's improve the focal planes as much as we can and see how far we can get. Okay, so here you see BICEP array with its 3 receivers, and this little receiver here is a heritage Keck receiver. So part 1 of this plan is to upgrade this receiver to maximum sensitivity, actually in a dual band receiver. The second part of this is an improved 4th generation receiver for South Pole telescope that'll allow improved delensing. And so these are forecasts that we made, and now I should say our forecasts are very much heritage-based. We know the efficiency factors and inefficiency factors from map making through years of observations, and our forecasts are always well-fitted, and have been borne out at least down to this level in terms of what we've achieved. You can see the bands coming in. Here's the new BICEP array receiver operating at 90 and 150 gigahertz. The new SBT receiver is not shown up here, but this notable kink in the curve is coming from improved delensing with the higher sensitivity SBT receiver. And so what you can see is that obviously we need delensing, but with this dedicated program going out into the mid-2030s with modest improvements in receivers and a lot of observing time, we can get down to of order 1 times 10 to minus 3 in the errors on R. And note the dashed line includes a foreground model with decorrelation in the dust foreground. The ultimate goal for CMBS4 is 5 times 10 to the minus 4, so that is getting pretty close to the goal. And to get further improvements, and even to get this improvement, it really requires a massive effort to get what are fairly small improvements in the ultimate sensitivity. So in conclusion, I just wanted to show this slide of forecast for where we might be for the CMB at 80 conference. And this forecast was generated by the CMB S4 team, and I need to explain a couple things. You're going to hear more about this in the afternoon from Charles Lawrence. But what you see here is Simons Observatory and SPO observing through the mid-2030s with some upgrades. So the 2 cases for SPO, the yellow curve is showing the upgrade. There's a range here in the sensitivities. Simons Observatory has 2 sensitivity models, and so you can see their forecasts going out to the mid-2030s again. But the important thing is both of these observatories are getting down to the level of, or can get down to the level with modest upgrades of 1 times 10 to minus 3. And they're actually quite complementary because we're going very, very deep. We're maximizing delensing. SO is more shallow. It's wider field, less reliant on delensing. So it's a nice complementarity. What you're seeing here with CMBS4, this is not the plan for the program. It's showing what CMBS4 would do to achieve its original goals by itself if it was all picked up and transported to Chile and operated in Chile. And so with great effort. CMBS4 can get down to its goal here, but it's happening by the mid-2040s. So CMBS4 is now in the process of reformulating its plans, and that report has gone to the agencies, but it hasn't come out yet, so there's not too much I can say about it, but I will say that the plan now incorporates prior work coming from these stage 3 experiments, builds upon them rather than works independently. And then finally, you can see the comparative sensitivities here with LightBird and a US study for a more ambitious space mission that was done by Shaul Hanani called PICO. And I just wanted to end with the final thought, which is we assume that that space will be slower and more expensive than the ground. But this full CMBS4 program here costs about $2 billion, and it takes you out to the mid-2040s. And so those assumptions aren't necessarily valid. And so with that thought, I will conclude.
Thank you, Jimmy. And so, unless there are immediate questions, Martina will talk about a more theoretical point of view. Please. Thank you.
Morning all. Let's shift a little bit back the focus on what the complementarity between ground and space can do for the science targets that all the community aims to achieve in the next decade. And let's start with this plot here, which I think is the best summary that we can have to highlight the complementarity between ground and space. This plot shows the constraints on the scalar spectral index and the density of baryonic matter in the universe as constrained by two different experiments, Planck in orange and ACT in blue, so from space and from ground. And similar plots were also shown by the SPT collaboration, but let's focus on this first. And you can see here that first thing, ground and space now have the same comparable sensitivity to cosmological parameters, so to the fundamental physics properties of our universe. And second, that these constraints are complementary to each other, as you can see visually by eye, and in some cases also orthogonal to each other, meaning that their comparison and their combinations are powerful keys to enhance our sensitivity and our understanding of the universe. Where this comes from? This comes from the fact that ground and space have access to different scales, different angular scales, and so can explore the imprints of fundamental physics on the CMB statistics in the different fields, total intensity and polarization, and over a different range of angular scales. This means that we can think of the complementarity as a comparison between what we can get from ground and from space, and this will enable powerful cross-checks of the different experiments, especially as we will see later, if we aim to constrain fundamental properties of the constituents of the universe, and so we would like to have redundancy in our probes to strengthen our confidence in the constraints that we get. But we can think of the complementarity also as a combination within probes, because if we combine these orthogonal constraints, then the combined analysis will shrink our error bars and therefore will enhance our sensitivity to cosmological parameters, but finally to the understanding of the deep mysteries of the universe. Let's remind ourselves where this complementarity comes from in terms of physical imprints. We have to remind ourselves that we are thinking about a field synergy, meaning that these different experiments can probe with different sensitivity the total intensity of the CMB statistics, but also the polarization, both E modes and B modes, and they can observe it over a wide range of angular scales where the different physical imprints can be explored. So just to give a few examples, so we know that if we observe the largest scales, we can have access to the very early universe physics, which has to be yet modified by microphysical effects, whereas if we move to the smallest scales that we can access more directly with ground-based experiments, in that case we can explore what the late universe physics is doing to the CMB statistics, and so where the microphysical effects are at play. And so just to name a few examples from the largest scales, we can learn the properties of the reionization physics, as we heard the past days. We can have access to the reionization bump in the tensor modes, whereas at the smallest scales we can explore what the content of the primordial plasma is and what the interaction properties of these constituents are. In the following, I will go deep on a few examples taken from these slides to showcase better what the complementarity between ground and space can do in learning the properties of the universe. And the first example, just to shift a little bit the focus from inflationary science to something related to particle physics, is the other holy grail of cosmology, because one of the main science targets of cosmological probes for the next decade is to provide the first ever measurement of the neutrino mass scale, well before laboratory experiments can do, and we know that we can do that with cosmological probes by comparing the amplitude of perturbations over different redshifts throughout the universe evolution. To do so, we have to know what the primordial amplitude is, and we can do that from the CMB, from the earliest probe that we can have, but unfortunately the primordial amplitude is not accessible from itself, but is convolved, as we heard and we will hear in the next panel, so with the imprints of the reionization optical depth. And so in order to disentangle the primordial amplitude and at the end have access to measurements of the neutrino mass scale, we have to know very well what the amplitude of the reionization optical depth is, as this plot is clearly showing, where we have the neutrino mass scale on the x-axis and the optical depth on the y-axis. We heard from Chuck that from ground we can infer the optical depth with pretty good sensitivity, but we also know that from space we hope to have the ultimate measurement of the reionization optical depth, and therefore be able to reach the limit in terms of disentangling, decorrelating these two parameters by combining measurements of the amplitude at different redshifts from ground-based observatories to measurements of the reionization optical depth from space, and therefore strengthening a putative detection of this fundamental parameter of the standard model of particle physics from cosmology. Then moving back to the early universe science, we have a couple of very trivial examples of why the complementarity between ground and space is particularly relevant. First of all, we have heard many times from Carlo that, of course, we are going after a number, which is the amplitude of the primordial gravitational waves, but more than a number, we would like to characterize the properties of the primordial gravitational waves over a wide range of angular scales. So we want to know the spectrum of the primordial gravitational waves, and for doing so, we would like to measure the BB spectrum over a wide range of multiples. And while from ground we have a clear and clean access to the recombination bump, from space we can have access to both the recombination and the reionization bumps. meaning that in the first place, if we have a detection from the recombination bump, measuring both the bumps from space will strengthen our confidence and the statistical relevance of the measurement. And second, that with a measurement over a wide range of scales, we will be able to differentiate between different physical models that will give you the same amount, the same amplitude in terms of the tensor-to-scalar ratio. And here you can see clearly that in these curves where the BB spectrum is plotted, we have different projections for different physical models that overlap more or less at the recombination bump, but are clearly distinguishable if we measure very well the reionization bump. The second reason why we would like to have complementarity between space and ground is de-lensing. We have heard several times that lensing is now the main cosmological contaminant to measurements of the primordial gravitational waves. And of course, while space can have access to the full range of multiples in BB, the de-lensing operation is much more powerful if done from ground-based measurements, as this plot is showing, where we have the gain in sensitivity to R as we move towards including more and more information for the lensing from ground-based observations. But the other reason is that aside from the lensing, we can think of alternative routes to constraining the tensor-to-scalar ratio that involves cross-correlation between space and ground observations. And some of these works, for example, Namikawa and Sherwin has discussed in the past. And these alternative routes can reach sensitivities that are comparable to standard techniques, including de-lensing, and therefore enabling additional cross-checks of putative detections.
Martina?
Yeah. And finally, we can move to beyond standard model imprints and remind ourselves that we can constrain beyond standard model properties, for example, primordial magnetic fields or violation of fundamental symmetries of the universe by combining the observations obtained at different angular scales, because of the fact that these models can leave complementary imprints on different scales, and therefore combining satellite, balloon and ground-based experiments will enhance our sensitivity to the fundamental parameters behind these phenomenological models. Let me just briefly retouch on cosmic tensions, just to remind ourselves that redundancy here is key when we would like to delve deep into cosmic concordance. If we have multiple probes, especially from multiple observational pipelines with completely independent analysis tools and completely independent observations, we will be able to move out from the table explanations that are experiment dependent. And so, for example, if we have cosmological probes that all agree on the same constraints on parameters that are in tension with other non-cosmological probes, then we can be sure that we have to look for non-trivial explanations or non-trivial discussions to explain what we find. The same is true for redundancy if we want to measure fundamental parameters of fundamental theories, if we have complementary experiments that converge on the same value for those parameters. For example, here I'm showing the interaction strength for models of interacting neutrinos as constrained by the recent ACT-DR6 analysis in combination and in comparison with other satellite experiments. Then we can again strengthen our confidence that what we see from cosmological observations is really stable and is really reliable. Finally, just one word on the fact that yesterday's foregrounds are today's and tomorrow's signal. With the combination of ground and space, we can characterize better and better astrophysical, galactic and extragalactic sources, and therefore we can open a new window to the understanding of physical phenomena at play at different corners of our universe. And just one example for all, from combining measurements of the reionization optical depth or the time when reionization happens and measurements of the duration of reionization from the kinetic Sunyaev-Zeldovich as we observe from ground-based experiments, we are able to understand better the details of reionization physical models. And, oops. I will leave you now with my conclusion slide, which is not a conclusion, but just a set of points that are aimed to stimulate some discussion. So, for example, are there any other science targets that we haven't thought about yet that will benefit from the complementarity between ground and space? In ground and space, now we have larger and larger experiments, meaning that we have overlapping communities. Are we sure, or how to make sure that the analysis of these overlapping communities are really independent, and therefore we can advocate or we can claim independency of results from these communities? Do we need additional tools or platforms of different kinds, from governance to analysis, to boost the efforts, the collaboration between these platforms? Do we need additional format simulations, analysis tools to coordinate among different communities to enhance the science reach of all the endeavors that we are that are at play now and will be in the future? With this, I will thank for the attention and join the other panelists. Thanks.
Thanks a lot, Martina. Questions right now? Otherwise, Masashi can take the lead here. Thank you. Martina, come over.
Okay.
I will leave my seat.
As the last speaker from this panel, I'm going to do two things. One is to reinforce some of the statements already made, and another thing is to discuss what we shall deliver and what kind of messages we shall deliver to our neighboring communities, which is becoming more and more important. I'm Masashi Hazumi from KK, and I also, from April, I accepted an offer to be a visiting professor at National Central University in Taiwan, where my task is to make a new CMB experiment group. Let me start from this slide I showed 15 years ago at one of the conferences in Kyoto. There I discussed this future CMB polarization measurements, and then I introduced the concept of powerful duo, meaning a relatively small satellite plus very massive ground telescope arrays. And the first thing I'm going to say is that realizing this powerful duo still remains the best strategy to me. And then, that's the first thing I want to say. And then here I put one Q&A, satellite needed if primordial gravitational waves discovered on ground. And the answer is, of course, yes, for better measurements. So that remains the same. And then driving scientific objective also remains the same, search for primordial gravitational waves. If successful, if we do see the signal, we a huge discovery, it will have huge discovery impacts, direct evidence for inflation, knowledge on the inflation energy scale, and first evidence for quantum fluctuation of space-time, arguably. And then it also gives us an insight on quantum gravity, including string theory. And then because of that huge importance, if you look at, for instance, the final report of the task force on cosmic microwave background in 2005, so-called WISE committee report, it states the following: detecting primordial gravitational waves would be one of the most significant scientific discoveries of all time. So this is a powerful dual strategy emphasizing this tensor to scalar measurement, ratio measurement, has had success in the competition. So the JAXA in their down selection chose LightBird, and also CMB-S4, as Jamie said, at the P5, that's high energy physics, particle physics community, selected the CMB-S4 as a top priority future project. So when Hitoshi Murayama gave a talk at CERN, someone asked, is this really high energy physics or particle physics? His answer was clear: yes, it is. And then so the high energy physics community really embraced the CMB. So that success on LightBird and the CMB-S4 were not because both have a wide range of scientific topics, objectives, which they do. It's not because of that. It's primarily, at least, because of the importance, huge importance of this scientific topic. That's what we should remember. And then that's how these projects are being sold so far. And then having said that, I'm not saying we should have a single purpose project. No. We should have, and we do have, a wide range of scientific topics. And then we need to pursue from now on, I'm going to tell that later, but we need to pursue some sort of best balance, emphasizing in some occasions the wide variety of scientific topics. In some other cases, this important topic. And then the next important target is delta R better than 0.001, where delta R here includes the statistical and systematic errors as well as the observer bias. And so here are a couple of plots from LightBird, and then as you can see, LightBird, as already described, it's meant to touch on both recombination and reionization bumps, whereas the ground projects are focusing on recombination bump. And the current limit, around 0.03, should be improved by an order of magnitude at least. And then the right-hand side shows the some counter, again from this is from LightBird, assuming a Stravinsky model, and then together with several models. And Andre yesterday discussed the newest act observation might have some significant impact in this R versus N sub S plane. And that's already, to me, one of the great sort of example of the synergy, space ground. And then here is a rationale for delta R getting down to 0.01. I mostly took this from Andre's paper in 2017. So first of all, we have a large discovery potential between 0.03 to 0.03 or so. And then if we don't see the signal, we spend a lot of time to tell agencies the implications of not seeing the signal. And if that's the case, still we can sort of reject the single field models with characteristic field variation scale of inflaton potential greater than the Planck mass. So that means we don't reject the entire inflation sort of picture, But this is to really test the well-motivated category of inflationary models, which, discovery or not, it's going to set the future course of cosmology. So that's a very important point. And then here is just a simulated light-bird B-mode map made by Yuji Chinone at KK. For simplicity, this is a cartoonish example. So we didn't put the residual foreground. However, the noise assumed here is after the foreground removal, including the penalty due to the foreground removal. So you can see if the R is like 0.01, you can see both recombination fluctuation and reionization fluctuation. So as Francesco said briefly, we had the MOU between CMBS4 and Lightbird, and then we have been working on 2 lines of analysis. One is to answer the question how CMBS4 can improve this R measurement by foreground cleaning using Lightbird multi-frequency data. And the second question is how well Lightbird can improve this tensor to scalar ratio measurement by delensing using CMBS4 data. I'm going to say I'm going to show a couple of slides on that, and then one thing I want to emphasize is that the current MOU focuses on the above 2 analysis. However, there are many synergies between CMBS4 and Lightbird to be explored, including systematic uncertainties, calibration, and detector development. In particular, the space agencies are aware of the ground progress, and then success of the ground projects does not necessarily give us a higher TRL. However, some issues on ground are really, we need to understand that. Otherwise, they might stop us. So that's really important point. And then, as you already heard, Francesco gave us current status of Lightbird reformation plan. So based on this powerful duo strategy, we have been really successful until March last year, and then last 12 months or so were rather tough on both Lightbird and CMBS4. So as you heard already, this KK in Japan said decided the new management actually came in April and then decided in September last year not to commit to Lightbird development, and then that's why we are now making a reformation study. But the good thing is that actually European people are even more excited to me, and then also if you look at the situation in Italy, INFN is supporting us, and then that's of course high energy physics, particle physics agency. So and then also young people are still very energetic for the studies. These are very real important things, and so is the case for CMBS4, in spite of the fact that NSF decided not to use the South Pole. The CMBS4 group was energetic enough to come up with a new configuration, all Chile configuration. So I do hope that both will overcome the current problems. And once again, that's sort of with different reasons, not because we didn't push the variety of topics. And then I don't need to repeat this ground space complementarity in a cartoonish picture, but I just want to say, although we kind of ignore balloon projects here, balloon itself has some unique opportunities. I just want to say that here. And then one page about foreground cleaning, because we had a dedicated session yesterday. I don't repeat that, but one thing I want to emphasize is that our scope is foreground cleaning, not a physical understanding of foregrounds. Physical understanding of foregrounds, including the nature of galactic magnetic fields and interstellar dust, is perhaps even more challenging, although it has its own value. And then, so that's something we need to tell, because sometimes we get a question from neighboring communities. The question is like this: how come you establish the signal if you don't know the physics of foreground? That's a question. And then we need to tell our scope clearly, repeatedly, in a patient manner. That's really important. And then, but having said that, requirements flow for CMBS4 and Lightbird are somewhat inevitably affected by this foreground uncertainties. We are making some efforts to try to decouple that uncertainty from our requirements flow as much as possible. But having said that, another thing I want to emphasize is that ongoing projects, including Simon's Observatory, will provide precious lessons learned on the foreground cleaning in coming years. And then this already Martina mentioned, but this delensing. But I just want to say this is a Lightbird example, 20% improvement. But remember, Lightbird also has a reionization bump where the this delensing plays, a very minor role. So, this delensing is really an interesting topic, and then this is a sort of an initial attempt that we do need to address some other issues, like our non-uniform scan strategy affecting the noise and stuff like that. We should do that sort of studies. Okay, so I have been so far focusing on this tensor to scalar ratio measurement, but let me just show this. Now the variety of topics. So Lightbird has reached scientific objectives beyond R: optical depth, reionization of the universe and neutrino masses, cosmic birefringence, mapping the hot gas in the universe, and isotropic CMB spectral distortion. We're not measuring monopole component, but we can do measure this spectral distortion anisotropic part. And primordial magnetic fields, elucidating spatial anomalies with polarization, galactic astrophysics. And Martina already covered important parts of that. And then here I took an example from a recent Simon's Observatory Large Aperture Telescope forecasting paper. But basically, this is also the case for CMBS4. This small aperture telescopes, or SATs, are more or less focusing on the tensor to scalar ratio, but LUTS has a broad scientific topic from the last scattering to our planet. So early universe, relic particles, neutrino mass, galactic evolution, blazars, and galactic science, Planet 9, and transient sciences. So these are all great. But going one step further, what I want to emphasize is that with these many measurements, you can really have a chance to see something unexpected. So in that sense, serendipity is essential at the same time. And then that serendipity becomes maximum when we combine, we think about the synergy between ground and space. Like comparing results from space and ground might lead to new anomalies. So even if, this tau, as an example, optical depth, of course, Lightbird E mode, lowest E mode, can give us a better value. But at the same time, SOLAR can use kinetics SZ, for instance, to have some better measurement than now. And then, no one knows if results agree. And then there are so many examples like that. And then this one was already shown by Martina. But here the emphasis is again space-ground complementarity. And then if you look at the recombination bump, probably ground has a better sensitivity. But still, if the signal is sizable, it's crucially important to see consistent power on recombination bump, and also the reionization bump power consistent with standard prediction. And if not, of course, that's going to be a big discovery. So, and then actually, if you can go on toward that direction, I took an example from this paper in 2021 by Paolo Campetti, Eiichiro Komatsu, Davide Poletti, Carlo Bacigalupi. So they discussed with basically the same action SU2 model. They argue that other gravitational wave projects like SKA, LISA, Einstein telescope can detect that signal that should be consistent with LightBird discovery. So that's also a great possible synergy beyond the CMB community. And then this is the last slide. I would say coherent messages about the space-ground complementarity from the CMB community to neighboring communities are necessary for large projects like CMB-S4 and LightBird. At the beginning, I showed my slide in 2010. From the beginning, my vision is not, ground or space. My vision from the beginning has been ground and space. And then to realize this powerful duo, we must address, of course, budgetary and technical challenges. And then, and also at the same time, we need to integrate ourselves into the academic ecosystem of the astronomical and high-energy physics communities. In this regard, the key is the support from neighboring communities, including the gravitational wave community. As shown in this plot, clearly, this B-mode measurement should be essential part of the exploration of the gravitational wave landscape. But my experience is in some cases, this leftmost part from CMB is just sort of ignored, and you see the plots without that. And then we should really coherent, not to avoid that happening again. And then to that end, a cooperation between CMB-S4 and LightBird is really, really very effective and important. So that's my message. Thank you very much.
Thank you.
So thank you. Now we have some time for discussion.
Okay.
I'm sure there are a lot of open ends to be taken. Paolo.
Thanks to all panelists for these very nice talks. I have actually two questions. The first one for immediate results from ground-based experiments in the next few years. We heard that the phase space of these experiments is widening also to the largest angular scale. So my blunt question is, how much of this future effort will have to rely on legacy high-frequency data from Planck, right? So how much is this relevant? And the second question is about optimal polarization modulation strategy. So we heard the first day that neither WMAP nor Planck were designed actually to measure polarization, but they did manage to provide results. So now for future satellite missions, not only LightBird, but also possible missions on the horizon, designing optimal polarization modulation strategies is critical. We heard from Francesco the baseline solution adopted for LightBird, and I want to know what the respected panelists think of the situation. Thanks.
So who wants to take one or the other question? Lyman.
I can start. For WMAP, actually, we did play with taking one feed and making it sensitive to polarization. But in the end, it would have been one that was different, and so it just absolutely wasn't worth it. But it's more in the, I'd say less in the observing strategy and more in the receiver configuration, right? You want to do everything you can to balance balance these two polarizations. That's what the half-wave plate does so well, right? It symmetrizes the beam and balances it. So I think it's more, you have to have you want a good cross-linked strategy. That will always win out, but the other is a better receiver configuration. For ground, Jamie, I think we...
large case from ground.
I think Planck is going to... Yeah, I think Planck will continue to play a huge role, I think, for many, many years. These high-frequency maps are brilliant. And, well, it's all brilliant, of course, but the high-frequency maps are just absolutely invaluable. And efforts will go, 280 gigahertz it's hard to observe from the ground in Chile. And
not so great from the
and
pole.
not so great from the pole, right? And the CCAD is endeavoring to put an antenna up another 1,000 feet on the top of Chajnantor, and that will help, but still it's limited sky and all the other issues you have with it. So, and it's not large angular scale. So I think we'll be using Planck for till CMB at 70, I'm sure.
Any more comments on these questions?
I mean,
Jimmy?
Well, I mean, as I pointed out, at least for the super deep measurements, we really had to do our own foreground measurements. But we are getting into an interesting regime where this power spectrum-based foreground subtraction will break at some point. And so I think, using Planck in maybe brighter regions is going to be informative to figure out, what's the optimal next step to add complexity to our foreground algorithm. On space missions, the question about control of systematics, I mean, I think it is interesting to note that you saw it in the Lightbird presentation, but obviously you want a lot of cross-linking, you want matched detectors, but there is a split as to whether you need a wave plate or can make the focal plane itself very, very 1/f stable like Planck was. And there's different approaches there and advantages both ways.
yeah,
Yes. Chris, and then...
Could you please comment somewhat carefully on what used to be in the past the critical aspect of interplay between ground and space, and it was technology maturation. So the core of that was always consideration of detectors. My simplistic understanding is that bolometers are essentially at quantum limit operation, and there are demonstrated technologies at JPL, for example, of reaching similar floor with low frequency detectors. So is there something we're missing? Because, these timescales for development of huge projects on the ground, as Jamie just demonstrated on the plot, so very, very long. That was always the worry. Going to space is going to be putting all technology on the satellite, and the ground will be ahead. But will ground be ahead? With that regard, detectors alone. What is the realistic assessment of the future development of detector technology? What would be on the satellite in 20 years? What will be on the ground in 20 years? Is there still time advantage to ground process, or space is safe from that point of view? Well, am I not understood? Or?
you start.
Okay, so I think there are a couple of technical challenges. One's a small one, but the detectors on Planck were not really photon noise limited. And so there's a little sensitivity to gain there to really tune that up. Okay, that's a small point. The other point, I think, though, is multiplexing. And especially for proposed ground-based experiments with 500,000 detectors, going with kind of low multiplexing factors because they're high technology readiness, well, that's been the choice of the field, but boy, is that going to be painful. And I think, if we had field demonstrations of RF multiplexing with higher multiplexing factors of hundreds or thousands. And I mean, not just RF mux, because then you have to build all those readout channels, squids, so it's not incredibly multiplex. But RF multiplex, like kinetic inductance detectors, especially for the ground, I think that would be a big step forward. But it's not ready yet.
I can say, at least from what I've seen, our detectors, I'd say the bolometers are not ready for space. They're sensitive, but the imbalance between the two polarizations is too large. And I have to admit, and so just I would echo what Jamie said, not just this time, but a while ago. I mean, the best thing for the detectors is to work on some AC bias or something like that, or to make them super stable. And if they're super stable and you spin fast, then you can ditch the half-wave plate. And that's huge in cost and complexity and everything. And I think a difference, right, if LightBird only has 1,000 feeds, if I were doing it, I wouldn't multiplex, because you can get it just saves you so much, right? The key for LightBird is going to be control systematic errors, and with 1,000 feeds, you don't have to, I mean, it's painful, a little painful, but not as painful as the complexity of getting all that stuff ready for space. So anyway, that would be my starting position. Yeah, okay, yeah. So, to someone who's actually working on it.
I'm not sure if I agree with your opinion, but anyway, putting that aside, another thing is for space use is better immunity against the cosmic rays, and that's missing in ground detectors. So we need some special development.
Okay, so thanks for your very interesting presentation. So my question is, how important do you think it will be in the future to have a common agreement among collaboration, to have a common pipeline to fit the data, maybe in a joint likelihood to really allow the phenomenologists to fit properly different probes from ground and space? Also, maybe this is also important now with different Planck likelihoods like Hilly-Pop that might be combined with ACT. But also in the future, with higher precision, do you think there should be an effort from the collaboration to allow to have this general agreement to fit the joint data?
Maybe Martina, you touched upon this point.
Yeah, thanks for the question. I think it's extremely important, and there are efforts in that sense. I would say even a step before, at the simulation level, it's key, and one of the points of the MOU between LightBird and CMBS4 is exactly to join efforts to have a common ground for simulations that are used to inform both the design of the experiment but also the next analysis steps. There is another side of that question, though, which is independency of the pipelines, because on one hand, you want to share as much information as possible because that helps the combined analysis, but at the same time, you want to avoid biases in the analysis and therefore have redundant pipelines that are put forward by independent groups is not a weakness of the field. As you say, there are multiple likelihoods, but I think that is important if we want to have stable and reliable results and something that can be trusted from the outside. So it's important to have a common ground, but at the same time it's also important to remind ourselves that redundancy, if there is enough person power, is also equally important.
Okay.
I want to add to that. I think the zeroth order thing is everybody should have to make their maps public, period. And right now, it's only, of the maps that we've been talked about, it's ACT, WMAP, and Planck. Those are, anybody can get them. And anyone can, the whole thing. And that's really important, because these checks, I mean, we're getting into such subtle effects, foregrounds. These checks are really important, and the cross-checks and different people looking at them and different pipelines, and anyway.
I think you can get the timelines too.
Yeah, there we go. And WMAP as well. Yeah.
So
Yeah, I'd just like to challenge this space ground-based complementarity idea, okay? Because, you know, in the end, you know, we have not got a clue what the value of R is. I mean, you know, if I had to ask a question in the inflation section, I would have asked Andre, how many nanoseconds did it take to find a model that would fit, you know, NS of 0.97? You know,
Two days.
Yeah, well, I mean, so, no, I mean, it's dead easy. You can easy to construct models with undetectable values of R. But it's a hard sell to sell a space mission when you don't have a target, and when the specific models really, you know, the number of people that would be really disturbed if you ruled out Starobinsky would not be very great. So my view actually is that if we're lucky, and R is sort of at the 10 to the minus 3 level or something detectable, it'll be done from ground. And so do that first, and then if you think that there's you know, once you've detected something, if we're lucky, that there's a case for a space mission, really fine-tune that space mission for that target and get all of the other science on E-modes and so on with a very restricted range of frequency coverage, make it as cheap and cheerful as you can, and do it that way. Okay, so ground first, space later. It's also a question for me, George. Give us some model that we can falsify. That's what we need.
That you won't ever get it. You won't ever get that.
Well,
Try.
I have to say that's a recipe for CMB at 100.
Yeah.
It's one problem. 20 years for the ground, then another 20 years for a space mission. I would like to do something sooner.
I wouldn't dismiss tau. I think it's going to take space to get tau to the level we want it to do all this other science that you know so well. Oh, I'm not so sure. To nail it with foregrounds, I mean, you've worked at LO4. It's hard, right? I mean, it's just like pulling hair, and you need so I think you're going to need all that frequency coverage. And yeah.
Just a quick comment on that. I completely agree with you, Jamie. You can't separate the two, and I'm going to say the main reason is because we have to keep a community together with a lot of very smart young people who will carry the torch for us. And the space aspect is fundamental as well as the ground, in my view. But that isn't my question. My question is, one of the things that's been rather unfortunate, in my view, is that any attempt from, let's say, North America or Europe, for that matter, to try and do a northern ground-based experiment has not gone. I mean, maybe when Greenland becomes part of America, who knows? But a place where it's happening is in China on the Tibetan Plateau. And that community is just in development. It is not the time politically, perhaps, except for Canada, to engage heavily with them in the US. But clearly, if we had a northern sky equivalent to the kind of things that we're getting from Chile and South Pole, then we would have complete overlap with the budding space experiments. And so I wonder if anybody wants to comment on the importance of that as, cross-correlation checks, et cetera.
Well, I certainly would like an all-sky lensing map for other things, definitely.
But it's happening. I mean, Yacheng Li is one of Suzanne's students who is now working on detectors in China that will make it into Ali. So there's cross-correlation and
Yeah, but the community is very, we have a very sophisticated community.
Yeah, no,
so a long way to go, but with collaboration, we can accelerate that if there's, copacetic interactions among nations.
Totally. Totally. It's starting, and I'd say it's starting. I mean, because Ali hasn't been around that long, right? But I think it's starting, and the opportunity, I mean, I should be careful here, but from my younger Chinese colleagues, the opportunity, if you want to work in China, the opportunities are incredible.
And there's no question that China will do pedal to the metal
Yep,
to get
it's
things done,
really,
which will change the equation for
Yep.
us.
and take advantage of it. It's great science.
That being said, which is very important, there is a Tenerife site where things are ongoing, although the altitude is not like Atacama, and then there is balloon flights, which we are not touching so much upon, but I don't know, Paolo, if you want to comment, but it's an extremely important element in the game, although not as used as space and ground, but it's a powerful intermediate step, especially with long duration pressurized balloons. That could be a great opportunity. We have many people that want to. I think you were first, Francois. Then we have Joe, Daniele, Charles, and I think it was Carlo. Then stop because otherwise we have no break.
So I wanted to have your point of view because I heard both very strong plea or suggestion that we want to do small, fast, well-targeted on one end, and then I can hear that sort of the same people sort of say, we want a unified platform that everybody can collaborate, a massive single pipeline. We don't want to have several likelihoods. So how do you put together the desire to be able to work in small steam and move forward fast and targeted, all what was said, which is good and desirable, with the other part where you also talk for just the opposite. So could you say how you arrange this practically, this co-petition, if you wish, which we had a lot inside Planck, by the way. So I'd like to hear your thoughts on this.
Comment it's there. I think there are two levels. One is the level of the instrument design, instrument planning, and one is the level of the analysis. So the instrument level, I think there is to be some limitation in the goals because otherwise, it will never stop dreaming something better. So you need to define a target and do the best for this target with a minimum effort or in time and cost. For what concern data analysis and merging and this, I think in this sense, strongly linked community is the key. I mean, there are a lot of a joint effort can be a key in this sense. So I think this can be done with a very high level of ambition.
Just one, I think it almost takes care of itself. I just look at these incredible tools we have now, CAM and Kabaya and all this, forgotten all the names, right? They sort of came out Heliopics, right? They came out very organically, and they won, and a lot of things were happening. You pick one, a bunch of people then are developing the next level, something emerges, and it's efficient, and it grows, right? And everyone just looks for the best tools. And so I'm less. It's architecture for computers, not quite. No, not quite that loose. Julian's just like shooting darts at me, but it's just there's some aspect of that. You need the environment. But in the environment, you want to let creativity grow and good things emerge if people feel free to innovate.
So I have a question which is more about science goals. We've heard a lot about, trying to search for the elusive signature of inflation from Armos, which may, as we've heard, may well be unattainable. But there is one thing one could be thinking about where there is a large amount of discussion, and these are the anomalies in the CMB, the north-south anomalies, etc., cold spots, whatever, and others, wouldn't they be a very important goal for especially a space mission?
Obviously, yes. And then I try to emphasize that in my serendipity slide. I don't know if I was successful, but it's really, really important. And having said that, how we implement that into our requirements flow, that's a different question. And then we certainly need to keep our requirements flow as simple as possible. But in our case, almost luckily, if you pursue this very good R measurement, many measurements are done in a good way. So that's sort of a rationale.
Just wanted to touch on the space-ground complementarity to attack systematics. So one of the major challenges for space is to do calibration of the absolute angle of polarization in flight. And we don't really have a solution, but on the ground, there's a wonderful campaigns happening, BICEP 3 using rotating a polarization source, these Simons using wire grid and drones. So if they nail some patches of the sky where CMB is absolutely calibrated, that's a universal calibrator for space. So I just wanted to know, BICEP 3 Simons or others, do you agree that this is a good strategy? And what is the current situation of these wonderful calibration campaign? Because that's a game changer. And that's really happening now. So I just wanted to know your thoughts and current status.
Yeah, well, it is hard from space to get the angles, and Planck developed a program, but it was a challenge. I think it needs further thought, but you may be right that you could take a calibrated angle from the ground and then map some bright region of galactic foreground or something like that, and use that as a way to translate to a space mission. But I think it needs further thought. Yeah.
At the point, I don't know what level you're talking about, but at the 0.1 degree, you can do the metrology. If someone's neither WMAP nor Planck were designed to do polarization, if that were in the requirements, you'd do the metrology, and you can do it well enough and have enough links so you could be pretty confident in the sky. I don't see a limit to that. I mean, not 1/100th of a degree, but 1/10th of a degree should be straightforward.
There are ideas also to have space-based calibrators that might be interesting in some future.
There is a project called
Cosmocal, yes.
In particular, this is now considered at CNES. The idea is to have a small thing that would be piggybacking on communication satellite, and essentially, unfortunately, this can only be done not for the South Pole, as a first option. But so this is proposed for actual things, and there are people in the audience, I hope, that can add on this.
Yeah, well, certainly the Spanish team was interested in this old idea.
Yeah, we have also a project to fly a microsatellite, maybe in the period of a year, in a heliosynchronous orbit. And this is just a small thing, and a prototype with only one source at the W band. And I think this could be also good for this calibration.
Okay, we really need to go to the last questions. Daniele, then Charles, and then Tomo, and that's it.
Okay, thanks, Marco. I have a question that regards the way to get and secure long-term funding in the context of B modes for the future. We know that we learned that the inflationary scenario doesn't provide a lower limit greater than 0. We've heard that a theory that allows falsification is not in sight. So I think that we should be prepared to the eventuality that at 10 to minus 3 one doesn't see anything. And so at that point, I think it is important to sort of change also the narrative that we have to follow when presenting these cases to who's going to pay for this long term. And so probably, well, I feel that we should emphasize more and more the importance of getting data, of the legacy value of the data, also in view of a situation where you really cannot claim that you can falsify a theory, and so if you make a certain measurement, you will get, for sure, a big result no matter what, because this is not the case. And so, yeah, this is what I wanted to stress from my point of view.
Comments?
Just a comment. I think both the PICO papers, the PICO work, and the recent SO papers are, putting a lot of effort in describing what else you can do with these instruments on top of the tensor to scala ratio. So I think this is very important, and it's in line with what you say. So a lot of data available for the community for many aspects on top of the tensor to scala ratio, as also Masashi mentioned in his talk.
That there is something for everyone. And so I think that was a little bit simplistic discussion about let's define something fundamental and everybody will agree to it. I think, at least in the areas of the world I know, it simply doesn't work. I mean, our colleagues in optical astronomy are less fascinated than our colleagues in particle physics. So we have to be a little bit careful about what we're selling. And I tend to agree with Agnello, that is, the legacy value of having full sky map, great control of systematic, all angular scales, and that can only be accomplished from space, hasn't been sold well enough.
I think it's safe to say for CMBS4, for Department of Energy, their number one science goal is inflation. I mean, that's their main interest, so there's the contrast, yeah. Right, in contrast, yes.
Right, so probably CMBS4 and LightBird are two special cases where high energy physics community really supported the projects. And then you are completely right. And that's one of the things I wanted to emphasize when you talk with astronomy community, for instance, and I just took SO as an example, and same for CMB S4. We really show the legacy and then a wide range of scientific topics and serendipity and things like that to get more people involved in that. I completely agree. Just I explained more or less what happened on LightBird and CMBS4.
It takes a lot less hardware in space.
Your mic's not on, I think.
Hello?
Yeah, just speak up.
It takes a lot less hardware in space to do what we're talking about than it does on the ground. And it used to be that space was so expensive relative to the ground that you'd make arguments about space as a last resort. But we have seen, Jamie commented on this morning, that has changed. We have crossed a threshold. The cost for CMBS4 was greater than the cost for something much more capable in space. That is a very important change. Don't forget it.
Good point. interesting.
There are a lot of things under the rug in that comparison. So, yeah.
Just very briefly to share the story inspired by the H.R.'s comment about the synergies between the ground and space for the systematics. Andrew Lang had the idea of calibrating Planck using BICEP data. So that was the synergies that he had in the idea. That came out to be, in the end, it's less for an angle, but actually detection of the CO leakage of Planck. So this kind of thing was actually happening in the past, and even came out to be more important than it was planned. And so I strongly believe that the synergies that we're thinking and planning can be good, but even can be even better than what we were planning. So I think it's important to keep talking. This is not so much a question, but just a story to share.
Okay, thank you, Tomo, for your comment. Any comment on this? We are really late, but that shows the interest in the discussion. So let's go to the coffee break and thank our speakers today.
Great job. Very good, the map. Thank you.
Thank you.
Thank you. I like the non-multiplexed.